Here we go. Reminder the other day we talked about exponential growth, exponential decay. Things that grow or decay exponentially, population was an example, bacteria growth was an example, both exponential growth. Now let's look at an exponential decay type problem. Reminder that we left off with a formula, APERT. APERT gave us an example of what happens when something, let you shoot in a second. What happens when something increases exponentially, such as when we're dealing with a bank, we had continuous compounding of interest. The same way that when you have exponential decay, that decay is continuous. Okay, that decomposition, is a continuous decomposition. So that's the reason the same formula kind of works in the same kind of way. Instead of APERT, though, we have A equals, they have A subscript 0. That simply means anytime you see that subscript 0, think back to physics, anytime you see a subscript of 0, that's an initial amount. So this formula, the amount of carbon 13 here, carbon 14, the amount of carbon 14 that you have is equal to your initial amount of carbon 14 times E, and a reminder that E is simply a number. E is approximately 2.718 times, so A0 times E to the RT power. R is your rate of decay, and T is the time in years. So reading this problem, it says, finely chipped spear points shaped by nomadic hunters in the Ice Age were found in the scene, or at the scene of a large kill in Lubbock, Texas. From the amount of decay of carbon-14 in the bone fragments of the giant bison, scientists determined that the kill took place 9,833 years ago. Carbon-14 is a radioactive substance that is absorbed by an organism while it is alive, but begins to decay upon the death of the organism. The number of grams of carbon-14 remaining in a fragment of charred bone from the giant bison after 2 years is given by this formula, where R is that. Find the amount present initially and after 9,833 years. That sounded really confusing. Here's your formula. A equals A0, E to the RT power, where here's your R, and T is, we're looking for the time. From the amount of carbon-14 in the bone fragments, science determined that the kill took place about 9,833 years ago. So instead of using this, let me scroll down. E to the negative 1.21 times 10 to the negative 4 power. T. And we want to know how much of this was initial, or how much of this carbon-14 was there initially in this what was it, a wood spear or something? On the death of, in this, what is it, a giant bison, there we go. Trying to figure out what, to find out how much it started with. That's where your time is equal to 0, your starting time. So all you got to do to find out how much began in this organism, simply plug in 0 for T. You'll see that this whole thing simply goes away, and you've got E to the 0 power. Help me out with that, Noah. What is E to the 0, or anything to the 0 power? Itself? No. Anything to the 0 is 1. So you have 3.6 times 1, which is simply 3.6. So at time equals 0, you have 3.6, is it in grams? Number of grams, yes. So initially you had 3.6 grams, but we are 9,833 years later. We want to know how much of that 3.6 gram has decayed over those 9,833 years. So we go back to our formula, we take out T, and we just simply plug in 9,833. And that'll tell us what it's decayed down to. So the amount now present is equal to 3.6 times E to the negative 1.21. I'll tell you what, times 10 to the 4th. Let's go back and review just real quick what it means, scientific notation. Negative 1.21 times 10 to the negative 4 simply means take your decimal and move it 4 places to the left. So if you want to write that as a decimal instead of that, that would be 0. Move it once, you're to the left of 1. We need to move it 3 more times, so put 3 more zeros. 1, 2, 1. Times time, which is 9,833. We simply type that into our calculator and we're done. So typing the whole thing in is simply 3.6 times, again, reminder that we have two different E buttons. You have one above this LN and you have another one over here. Use whichever one. If you want to use this one over here, it just doesn't put the little caret up there. You have to do it yourself. That's the only difference. I don't know why. So you have negative 0.00012 times 9,833. Enter. 1.106, so about 1.1 grams is left. So we started with 3.6 grams after 9,833 years. We're down to 3.6 grams. Again, let me show you this. Here's the graph of what we just did. It's an exponential type graph. Remember what exponential decay looked like the other day. Okay, and it tapers off at normally 0. Will there ever be 0 grams of carbon-14 left in this item? No. Okay, the way it decays, at the rate it decays, now you could be very close to 0, but you'll never have 0 grams. So theoretically, you should always be able to tell how much or how old this thing is by using this carbon-14. Moving on, let's talk about logarithms. Well, this might be your first look at what a logarithm is. Don't get bogged down with logarithms. A logarithm is simply another way of writing an exponent. That's all it is. We all know that, let's do a simple one. 3 to the second power is equal to 9. A logarithm is simply another way of writing that exponential or that exponent form. Here's how you write it in logarithmic form. Log, and here's how I always remember it. The base of the exponent, 3 is the base, 2 is the exponent. The base of the exponent will also be the base of the log. So this exponential form could be written as log base 3 of whatever this number is over here is equal to your exponent. You can go backwards and forwards between logarithmic form, exponential form. Again, a log is simply another way of writing an exponent. Don't get bogged down and confused as soon as you see that word log. 5 to the third power is 125. Is the exact same thing as saying log base 5 of 125 is 3. 5 to the third power is equal to 125. Again, I call this the base, and most of the time I just call this the argument. And that, of course, is the exponent. Any questions? Evaluate each log. Log base 3 of 9. If you need to write that equals x, on there you can. And simply change its form. The base of a logarithm is the same thing as the base of the exponent. The number on the other side of the equal sign is your exponent. So rewriting this, Tootin, can you rewrite it for me? In exponential form. This is, again, called logarithmic form. Could you write that in exponential form for me? 3 to the x power is 9, and he's answered it for us. X is 2. 3 squared is 9, so x must be 2. Next problem, log base 2 of 1/4. And again, if you need to put the equals x just to where you can rewrite it in logarithmic form, Logan, help me out. 2 equals, that's it. 2 to the x power equals 1/4. Now we've got to solve that. We know that 2 to the second power is 4, 2 to the third power is 8. That's getting bigger and bigger and bigger because it's exponential. We need to go the other direction. 2 to the 0 power is 1. As soon as you start raising this thing to negative powers, you're bringing it to the bottom of a fraction. Negative 1 would be bring the bottom, that'd be 1/2. So x must be, anybody? Negative 2. Good. 2 to the negative 2 power, just a reminder. Need a fraction bar, bring it to the bottom, it becomes 2 to the positive 2, so that would be 1/4. Log base 1/2 of 8. Daniel, rewrite this thing for me. Equals x. 1/2 to the x power equals just your 8. We're going to have to do the same thing. We don't need a fraction raised to an exponent. We need a whole number. So your x value here is going to be negative. That's going to flip this. So now you have 2 to powers. 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8. So therefore 1/2 to the negative 3 would flip it and raise it to the third power, which would give you 8. Notice on this next problem, there's no base. Okay? If there's no base, excuse me, this is known as a common log. One that you would find in any neck of the woods. A common log. A common log will always have a base of 10. Common logs, if there's no base there, it's understood to be base 10. So therefore, if you need to rewrite this, this is simply log base 10 of 1,000. Or you're asking yourself, 10 to what power is equal to 1,000? 10 to the first power is 10, to the second power is 100, 10 to the third power is 1,000. So log base 10 of 1,000 is 3. Let's look at our calculators. Your calculator has a log button on it. Okay? My goal in college, one of my goals, was to learn what all those buttons did. So now you're one step closer, if your goal is the same. You now know what the log button does. LOG. The log button on your calculator is a common log. Okay? You can't find, well you can, but we're going to have to talk about how to do it. You can't type in just straight log base 3 of 9. You have to kind of, there's somewhere you can find that on there to where you can type it in like that. But the logs that are on your calculator, when you hit that log button, there's no base there. It's understood to be log base 10. So could I work this problem in my calculator? Sure. Would I need to? I hope not. Log of 1,000 is 3. Because that's simply saying 10 to what power is 1,000, and it is 3. You could type in log of 1,000,000, and hopefully you would know that would be 6. Because 10 to the 6th power would be 1,000,000. Okay? Moving on. LN. This is called a natural log. If it's log with no base written down there, it's understood to be base 10. If you have the letters LN, that is a natural log. I don't know why it's not NL. I guess it's Latin. LN is a natural log, so you're simply asked to find the natural log of 1. If the base, see if anybody's a good guesser in here. If the base of a common log is 10, what would the base of a natural log be? Here it comes again. The base is E. Here comes that E stuff back. The base of a natural log is E. E is the number approximately 2.718. So if you would like to rewrite a natural log, you're simply asking the log base E of 1 is equal to question mark. Or you're saying E to what power is 1. How do you raise a number? Because again, E is simply a number. It's 2.718. How do you raise 2.718 to a power to give you 1? Carly, what would that power have to be? E to what power is 1? 2 to what power would be 1? 3 to what power would be 1? Careful. 2 to the 1 would be 2. 3 to the 1 would be 3. How do you raise something to a power to give you 1? Does anybody know? Power has to be 0. Natural log of -6. Again, you're simply saying, okay, this is base E. You're saying E to what power equals -6? That's all this problem saying. 2.718 2-watt power is equal to negative 6. You can type these straight into your calculator. Like on the last problem, I didn't tell you, but there's an ln button as well. You have log base 10 and you have log base 2 on your calculator. So I could type that straight in. On the last one, I could have typed in the natural log of 1 and it gives me 0. Okay? I type in the natural log of negative 6, ln negative 6, and it gives me error. Non-real answer. Why? Think about what, well, we haven't done logarithmic graphs yet, but think about what this looks like. E to the x power, or just some number to the x power equals something. Y equals some number to the x. Remember, it looked like this. And you had an asymptote line there at 0, and it never crossed. The reason it never crossed is you raise a number to the 0 power, you get 1. Raise it to the first, second, third, fourth, fifth power, and it starts growing. Raise it to negative numbers. Okay, how do you raise stuff to negative numbers? You bring it to the bottom. So that's like 1 over 2.718 is close to 3. Just for technical reasons, let's call that's about 1/3. E to the negative 2 is 1 over e squared, which is about 1/9. E to the negative 3 is about 1/27th. 1 over 81. So when is that ever going to be negative? It won't be. How can you raise a number to a power and give you a negative number? You cannot. Okay? A number to a power will never be negative. So therefore, what's the answer here? No solution. Which brings up a good point. You cannot log or natural log a negative. Not only can you not log or natural log a negative, you cannot log or natural log 0 as well. How do you raise something to a power and it equals 0? 0 is actually your asymptote line for that. It will never hit 0. So you cannot take the log or natural log of a negative or 0. So what is that going to lead us into? That whole domain range stuff again. If I give you a logarithm type problem and I say, what is the domain of this? You would have to say, well, the stuff that you're taking the log of can't be 0 and it can't be negative, so it has to be greater than 0. Sketch the following graphs, y equals 2 to the x and y equals log base 2 of x on the same coordinate system. Before we do that, let me show you why we're doing it. Y equals 2 to the x, and we're going to sketch y equals log base 2 of x on the same axes. Henshaw, change forms here for me. This is in logarithmic form. Remember what I told you, and maybe it's easier if I put the y at the end. That's how you used to see it. Log base 2 of x equals y. 2 is the base. Change forms for me on this if you can. 2 raised to the equals, good. Everybody understand how he did that? Or, let me flip-flop that back around now. X equals 2 to the y. And look at those two things. Y is logarithms thrown into this chapter. Y equals 2 to the x power, x equals 2 to the y power. Back about two or three chapters ago, we talked about something called inverses. To find the inverse of a function, we took our x's, we took our y's, and we flip-flopped them. We switched them. Y equals 2 to x equals 2 to y. Is that not the exact same function? Flipped. Y equals 2 to the x power and y equals log base 2 of x are inverses of each other. When two things are inverses of each other, and this is hopefully a little review for you. If two things are inverses of each other, they are symmetrical about the line y equals x. Here is y equals 2 to the x power. Here is y equals log base 2 to the x power. Or excuse me, y equals log base 2 of x. They are symmetrical. The first one, when you plug in 2, you get 2 to the second power, which is 4. If you do log base 2 of 4, that's 2 to what power is 4? You get 2. Okay, they go backwards and forwards between each other. They are inverses. The same way that y equals 3 to the x and y equals log base 3 of x would be inverses of each other. Y equals e to the x power would be inverses with y equals natural log x, which would be y equals the log base e of x. Those are all inverses of each other. Y equals 10 to the x power would be inverses with y equals just plain old log x. Because we know that this log base is 10, those two would also be inverses of each other. But let's go back to what the graph, or what it actually asked me to do here. Sketch the graphs y equals 2 to x. We won't actually sketch because I've got it down here, but I do want to do the second part of that. State the domain and range. The domain. Domain, there we go. The things that x can be. What all can we plug in for x? Can we do 2 to the first power, 2 to the second power? When you ask for domain and range, and that's what, if you don't get anything else out of this lesson, go back and review that stuff about domain and range. Domain and range is simply what can x be, and when x are those things, your range is what would y turn out to be. What can I plug in for x? Can I do 2 to the first power? Can I do 2 to the second power? Can I do 2 to the 1 millionth power? Sure. Can I do 2 to the 0 power? Yes, it's 1. Right? Can I do 2 to negative powers? Yeah, because 2 to the negative 1, you bring it to the bottom, flip it. So what can I find 2 to the power of? Somebody want to help me with the domain here? All the values from negative infinity to all real numbers. You can find 2 to any power. This is different. When I plug those values in, think about what the graph looked like. 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. 2 to a power, think back to what I just a while ago told you, 2 to the power of anything will never be, what? Negative, and it will never be 0. So therefore, my range starts at 0 and goes up. And you see that by your graph, because we know from Friday's lesson you have an asymptote line at 0. Here's 2 to the x power. You can plug in anything, but it'll taper off at 0 and it'll never cross it. Well, now it's easy. Watch this. Domain. Zero to infinity. Range. Negative infinity to positive infinity. How did I do that so fast? They're inverses, just told you. Your x's and y's just flip. Your domain and range simply flip. And does that go along with what I told you? Yeah. You cannot take the log of 0, and you cannot take the log of a negative. That's the reason your domain here, the things that you can plug in, start at 0 and go to infinity. You can never take the log of a negative or 0. Done. Next, we're doing the same thing. And then we'll just look at the sketches that I've got down here. Log base 1/3 of x equals y. You cannot take, okay, domain first off. The log 1/3 of x, it doesn't matter what the base is. You cannot take the log of a negative, and you cannot take the log of 0. So there's your domain. Your range, when you plug in 0, or you can't plug in 0, when you plug in the next number closest to 0, 0.00001, 1/3 of what power is that? You can actually plug those values in if you want to, or let's look at the graph. Or if you want to do this might be easier too. Rewrite this thing. That'd be x equals y to the 1/3 to the y power. Maybe it's easier to get domain and range there. When you raise, well, y equals, let's do the inverse of it, 1/3 to the x power. When you raise 1/3 to the x power, what values do you get? Because you can raise it to any power, well, that's what I need you to know. Is what values could y be? Y can be anything. From negative infinity to positive infinity. So when finding domain and range, sometimes if you play around with it, switch your x and y's, find the inverse. Just keep in mind that when you did that, that you switched your domain and range. But when you changed forms, this right here is saying the exact same thing. When you change forms and ask yourself, what values could y be? I can raise 130 any power, so y can be anything. Y will range, and you see that here. It goes up forever, it goes down forever. Now it's going down a little bit slower than it's going up, but it is going both directions forever. We're doing this, like I said, with every chapter from here on out. We'll introduce a new function. Even when next chapter we're getting into trigonometry, deep into trigonometry. What will we do? We'll introduce sine, cosine, tangent, and then we'll look at the graphs, then we'll look at transformations. We'll introduce secant, cosecant, and cotangent, then we'll look at their graphs, and then we'll look at their transformations. So know this transformation stuff. If you learned it the first time, it makes it so much easier the rest of the year. There's only one basic transformation here. It occurs there. Y equals log base 2 of x looks something like this. This is your parent function, by the way, log base 2x. That's simply the inverse of x equals log base 2 of y, which is y equals 2 to the x power. So 2 to the x, we've done that. Here's what 2 to the x power looks like. Here's what... I always have trouble drawing this. There we go. That's what y equals log base 2 of x looks like. Okay, this is your basic parent function here. Y equals log base 2 of x. There's been one transformation applied, and that's simply a minus 1. That minus 1 is on your x. Savannah, what would that minus 1 do? Moves your graph right 1, that's it. So, if you want to memorize what a logarithmic graph looks like, it's the same as an exponential graph. I always have to think of it like that. I know what y equals 2 to the x power looks like. That's easy because you have 2 to the zeros, 1, it grows exponentially, and then it tapers off at 0. This graph here, log base 2 of x, is simply the inverse of that. And reminder that an inverse is simply that same graph flipped across the line y equals x. So instead of having this graph, you've got it flipped across, you've got this graph. And then the minus 1 simply takes that whole graph and moves it right 1. Done. Transformations. Y equals negative 1/2 log base 2 of x plus 3. There are 3 transformations there. Let's go over all 3 of them. Colby. High school RV. Let's look for horizontal translations first. Colby, what does that plus 3 do? Moves your graph. Not up, but look, it's in the x. It's with the x, so left 3. Okay? Anytime it's in with the x, it's going to move it left, right, and it's backwards from what you think it is. It's going to move it left 3. Allie, do you remember what the 1/2 does? The 1/2 is not inside with the x. The 1/2 is being multiplied by the whole function. Multiplication is going to shrink it half as tall. Good. Not half as wide, but half as tall. The reason it says tall instead of wide, this is wide, this is your x, this is your left, right, this is your y value, this is your up, down. So it's going to make it half as tall. And then the last transformation is that negative. Brianna, what do negatives do? It's going to flip it down. Okay? Flip it down. I think that's what you meant by go down, right? So here's your original graph here. This is y equals log base 2 of x, and we had 3 transformations. We moved it left 3 to here. We made it half as tall, which kind of took and pushed it in from the bottom, pushed it in from the top, so it kind of squished it, and then we flipped it across the y-axis. Or excuse me, flipped it across the x-axis. We flipped it vertically, up and down. Okay, staying on the same thing, but we're off graphs now, is we're given some, I don't know why this is in here. We're fixing to get into some logarithmic equations, but again, this is just more of the same. To be able to go from logarithmic form to exponential form, we've already done that. The base of the logarithm, which, let me correct an error real quick before we start doing it. On your paper, when you're writing these, do not write it like that. This 5 is called a subscript. Same way that an exponent is a superscript, that 5 in the logarithm is a subscript. Write it below the log. So you have log here. The subscript goes down here. Okay, just so I know, is it a subscript, is it a superscript? It's kind of like an exponent in reverse. So make sure that when you write that log, or the base of the log, it goes down here. But to rewrite this, it would simply be that base raised to the exponent, so it would be 5 to the 4th is 625. Just know how to go backwards and forwards from logarithmic form to exponential form. That would be 3 to the 5th power equals n. This would be log base 3 of 50 equals x. Log base e. Okay, I do want to work this one. Log base e, how do you write log base e? Does anybody remember? What is log base e? Ln, natural log. Ln or natural log. So anytime instead of log base e, instead of can you put the e down there? Sure, it doesn't really matter. But to know on your calculator that goes along with the Ln button, log base e of 9 equals x minus 1. That's how you rewrite that. Now, that kind of brings us into the whole purpose of having logarithms. Your original function, or your original equation was e to the x minus 1 power equals 9. Can't you type this into your calculator? Isn't that just a number, ln of 9? Sure. Can you move the minus 1 over by doing plus 1? Can you solve that equation? Yes. Does anybody in here know e to what power is equal to 9? Probably not. The whole purpose, and I'm kind of going ahead and introducing it to you, the whole purpose of logarithms and natural logarithms and common logs, the whole purpose is to solve solve exponential equations. 5 to what power is 10? There's a trick question. 5 to what power is 10? Does anybody know? Don't say 2. 5 to the second power is not 10, right? 5 to the second power is 25. 5 to the first power is 5. It's somewhere between 1 and 2. How do we know what that power is? By using logarithms. That's where we're headed. That's the direction we're headed in. Okay, we got enough time to do this. Since we were discussing inverses a while ago, let's go back and remind you on how to find f inverse. Okay, and again, hopefully you see a trend. We introduce a new function. We go ahead and go into its graphs. We go into transformations. Now let's talk about the inverses of it. To find an inverse of any function, you simply have to switch x and y. It's done. That's it. Okay, to find an inverse of a function, you switch your x with your y, you switch your y with your x. Finished. So you have y equals 1/2 times 6 to the x minus 3 power. The inverse of that would be x equals 1/2 times 6 to the y minus 3 power. You can nearly circle that, finish. That is the inverse, but I really don't want to leave it like that. Let's solve it for y. The hard part of this is not finding the inverse. The hard part of this is figuring out what y is equal to, getting y by itself. First step, take the 1/2, move it over. Elizabeth, since 1/2 is being multiplied times this stuff, how are you going to move it to the other side? Flip it and multiply, that's right. It's going to be 2, right? You're going to divide by 1/2, which is the same thing as multiplying by 2. So that turns this into 2x equals 6 to the y minus 3 power. We're a step closer. Is there anything else you can move over? And you're getting a lot of good logarithm work from these problems. Can I move the 6 over and just leave y minus 3 floating in the air? No. No. You can't just move the 6 over and leave stuff up in the air. So here's how you do it. Once you get to this point to where nothing else moves over, change forms. Get really good at changing between logarithmic form and exponential form. That doesn't look like the basic form that you're used to seeing. If you need to, come over here and write it as like 8 equals 2 to the third, and ask yourself, how would I change this form? That would be log, the base of the exponent is the same thing as the base of the log, of the argument is equal to the exponent. 2, the 8 is the argument, and then there's where the exponent goes. So let's try to do the same thing here. Log base 6 of 2x equals y minus 3. Change forms. Now you can get y by itself. Don't leave it floating in the air. Change forms, move the 3 over, and you're going to have y equals, we can now say f inverse equals log base 6 of 2x. To move minus 3 over, we're going to do plus 3. Be cautious, though. I wrote that way for a reason. Be careful what you're taking the log of. This minus 3, when you move it over, is not inside. I could have put it in front, I could put it back. That's not what you're taking the log of. It's the log of this stuff. So therefore, do one of two things for me. Either put that in parentheses so I know log base 6 goes with the 2x. The plus 3 got moved over later. It's not inside there. Or you can write it as 3 plus log base 6 of 2x. Do one or the other so that I know where is that 3 supposed to be located. So that's the inverse. How can I check inverses? You should be able to take a number, such as 4. Plug it in, see if you remember this. Plug it in for x, that's 4 minus 3 is 1, 6 to the first power is 6, half of 6 is 3. So 4, 3 is located on your original function. That means that the inverse of that, 3, 4, should be located on your inverse function. I should be able to plug 3 into this and it carry me back to 4. Log base 6 of 6 is saying 6 to what power 6? That'd be 1. 1 plus 3 is 4. It does work. These are really easy. Solving logarithmic equations. Log base 3 of x equals negative 2. Here's your only rule. Clean it up as much as you can. Once you get it cleaned up, change forms and see if that helps. There's no numbers being multiplied by the log. There's no anything else happening. There's really nothing you can do here but change forms. Log base 3 of x equals negative 2. Jordan, help me change forms here. Base of the log is also going to be the base of the exponent. So 3 to what power? Careful. 3 to the negative 2 equals x. Oh, that helped. Right? That's very simple. Okay, so clean it up, change forms. So since x is by itself, since x equals 3 to the negative 2, well, 3 to the negative 2 is 1/9. Fraction bar, bring it to the bottom, raise it to the positive 2 power. So the value of x is 1/9 there. Log base x of 5 equals 2. Change forms for me, Trevor, because there's really nothing I can do besides that. What do you have?
X to the second.
That's it. So you took and you've turned log base x of 5 equals 2 into a basic quadratic equation. To get rid of the square, move it over to the other side and plus minus the square root of the other side. The only issue again, the base of a logarithm cannot be negative. So therefore we're going to throw one of those answers out. We can just do this. X equals the square root of 5. So again, the base of a logarithm cannot be negative. The base of a logarithm cannot be 1. And you can't take the log of a negative. 5 to the x power equals 9. Now we're getting into something. 5 to what power equals 9? And I'm going to go ahead and show you how to plug this into your calculator. Does everybody understand 5 to the first power is 5. 5 to the second power is 25. But if you run across something like this, 5 to what power is 9? There is a number exists that will give you this answer. And it's somewhere, it has to be somewhere between 1 and 2. Here's how you find it. Step number 1, clean up all you can. You cannot move the 5 over because, again, if you move the 5 over, x is floating in the air, and I have no idea what to do when x is just floating in the air. So let's do this. Change forms. Log base, let me change it, Dalton. Log base, what would be the base? Just change forms on this like we was doing before you left. Log base, base of the log is the same thing as the base of the exponent. So log base 5 of 9 is equal to x. X is by itself. The only issue you have is how in the world do you plug that into your calculator? And I'm going to get ahead of myself and we'll talk about this later, but it's called the change of base formula. Log base 5 of 9 can be rewritten. I don't want log base 5. I want log base 10. I want log base e. That is the only two that my calculator knows. So that's what I need, not log base 5. You can change a logarithm to any base you want by doing what I'm about to show you, and it's extremely simple. Simply rewrite it as log of any base you want of this number divided by log of that same base of this number. Just type it in like that. And notice I said log of any base. If you'd rather have changed this for some reason, your log button doesn't work, but your ln button does work, you could change it to any base. You could also have rewritten that as natural log of 9 divided by natural log of 5. One person type in the first, somebody else type in the second for me. Actually, I'll type in the second. You type in the first, log of 9 divided by log of 5 by using this button. And like I said, I'll type in natural log 9. Make sure you close parentheses, divided by natural log 5, enter. 1.365. You'll get the same thing for regular log. Same answer, right? So what does that mean? 5 raised to this power should give me 9. Let's see. 5 raised to 1.36521 2389. That's enough numbers. And you get 8.99999. Okay. Why do I not get an exact answer, guys? This answer here is not even exact. This answer is irrational. That value keeps going forever. But that gives you an extremely close approximation for what value you raise it to give you that 9. Now this would be exact. This would be exact, but as soon as you type that thing into your calculator, all of a sudden now you have approximate. So any questions on how to do that? Let's do another one of those, and then we'll pick up there tomorrow. 6 to what power is 37? 6 to what power is equal to 37? First step, move over anything that you can. There's nothing to move over now. Let me address this. Had there been like a 2 times something over here, you'd move that 2 over first. That 6 to the x power stands alone. It's by itself. When you multiply by 2, you can move the 2 over by dividing by 2, but it's not. But just in case you run up one on your homework like that, move anything over that you can. If there's like plus 3 tacked on the end, minus 3 first. Okay, move over everything you can to get it in this basic, most basic exponential form as you can. Next step will always be change forms. This will be log base 6 of 37 equals x. X is now by itself. And you simply have to type this in your calculator. The way you type this in your calculator is with the change of base formula. Change of base formula says you can use any base you want to as long as you write it as the log of whatever base of this number divided by the log of that same base of this number. Let's just use base 10. That'd be the log of 37 divided by log 6. Like I said, you should get something really close to 2. Biggest thing that I have for you is make sure as you type it in, log 37, don't do this. Don't type in log 37 divided by log 6. That will give you the wrong answer. The reason why that will give you the wrong answer is because it's clumping this whole thing. It's finding the log of this whole thing then. Okay? You only want the log of 37 on top, so you do have to close parentheses there. Right there. Second insert, close parentheses. So log of 37 divided by log 6. Get into a good habit of closing those. You do get 2.015. Now, how do you find... You can do 6 to the second, 6 to the third, but how in the world do you do 6 to the 2.01 power without a calculator? I wouldn't even try. But you have done some similar ones, like 6 to the 3/2 power. You've done rational exponents before. You've never done irrational exponents. I don't know how you do irrational exponents without a calculator. But 6 to the 3/2 power, remember the bottom numbers are radical, top numbers are power. So it's kind of that same kind of thing. To where you have an irrational exponent 6 to the 2.01, you could do the 0.01 is like 1/100, okay, and treat it like a radical. So that's where that comes from.